So Bodo AI is a startup. This presentation is about that and few of the innovations and technologies we developed under the hood. I'll start with a quick introduction of myself. I'm managed engineering org. I'm based in Seattle. My name is Ahmad Khadem, and I joined Bodo about 6 months ago. I'm super excited about what's the direction we are going to, and about the Bodo and how it's helping its customers and engineers. So I want to start this presentation with a problem, and the problem is the data engineering space. There are various tools and technology, lots of them, the dominant one are basically Snowflake, Spark, BigQuery, and doing customer interviews and talking to a lot of data engineers and developers, we have found that there is a kind of a growing pain of kind of a cost and execution runtime, even with Snowflake and of course with Spark, is that their bill is continuously growing, the cost is continuously going up, and the execution time slows their development life cycle. So Bodo is specifically built and emerged from high performance computing research and is approaching the data processing from a performance first perspective. And that's kind of the essence of a lot of conversations we'll have in the following slides. So the reasons that our current customers and the enterprises that we are collaborating with as part of POC and private previews, and in the future, we're hoping to scaling it to a lot more enterprises. The reason that they're using Bodo or they're excited about this is basically we are offering them massive performance improvements. So a little bit of a kind of a high level context. We are a cloud agnostic. Today we run on Azure AWS. We are hoping that we can run on GCP in 2023. For one of our enterprise customers, we are actually running on on-premise too. Adding a little bit of context on that is that it's your data stays in your own infrastructure under your own VPC, and all the compute infrastructure that we provision can stay in your VPC. So basically, our customers do not need to move their data or infrastructure into a specific cloud platform or like Bodo Cloud Platform. They can stay in their private network. So we support different kind of data warehouses. We are currently we can integrate with ADLS, S3, Snowflake, and we support different table formats like Iceberg, which is a kind of a new trend. And we work with Parquet and CSV, of course. So today, the way that our current customers and developers can write their code and processing code is like through Python and SQL. We more or less support standard SQL, so there's not a lot of disruption there in terms of like changing the code. The exact same thing that runs on Snowflake or BigQuery can run on Bodo, and Python more or less the same. There are some minor modifications you need to make in the code to add some jet decorators, but we support a majority of Panda and NumPy, so it should be more or less the same experience as the serial Python program. So basically, right now, today, we are focusing on compute. So we are offering a completely brand new compute engine, and we think that compute is the biggest kind of a pain point and the biggest cost in data processing. A big part of companies like Snowflake's revenue is through compute. But we are also thinking that in order to improve the customer experience, provide this kind of a seamless end-to-end data processing experience in the future, in our vision, we want to also think about kind of supporting the store layer so that we can offer this full data platform for even more seamless experience. So today we are 22 engineers, 33 employees. We're backed by Dell Venture Capital, Snowflake, Xilinx, and a few other ventures. So that's kind of a high level about the company. So some performance benchmarks, just to kind of showcase what's the scale of performance improvements you're talking. Are you talking about like 10% improvements, 20% improvements? I think the scale is the performance improvements we're talking is a lot more. So for some of the benchmarks like TPC-BB, which is a very compute heavy benchmark, we are giving like 20x performance improvements over open source Spark, which is running on 125 server nodes. On one of our, this is just coming from our own POC, like one of a retail customer, their pain point was that Spark being too slow for them. They were doing kind of a real-time analytics. And with Bodo, they got like 12x performance improvements, so they're going from more than an hour to 6 minutes. That kind of helps their pipeline to run more efficiently and faster, developer efficiency, and also like saving a lot of cost. So some context to add is that a lot of like the POCs, I don't want to bring too many data points here, but a lot of POCs we have done, we're thinking about like 3x to 50x. One of the companies that right now is going to production with us is basically seeing more than 40x performance improvements under a Snowflake SQL job that runs on a weekly basis. So we are definitely looking at loads that are a little bit more compute heavy rather than IO heavy, because that's where we can provide the best performance improvements. And also the other thing that's important is that the data size that the customers are kind of using, it's basically large enough that kind of makes Bodo or like migrating to Bodo more feasible, or let's say effective, I guess. So that's some of the performance improvements. So how does the code look like exactly? What does interacting with Bodo exactly mean? So Bodo code is more or less the exact same code that you write in Python. It's like, look at this example code. It's basically a Panda, read Parquet, do some regex, and the only difference here you see is that you're adding a jet decorator on top of the function. You see down below is like conda or pip install Bodo. You install the Bodo on your machine MPI exec. You don't have to do any of that right now because we have this Bodo platform. It's basically clicking a button. Creation of the cluster is all forms. I invite you all to go to platform.bodo.ai, try it out for yourself. So this code is like in our platform, we have the Jupyter notebook, so you can write the code in Jupyter, choose the cluster, run it, and it's very seamless. And for SQL, it's exactly the same experience. You are in Jupyter notebook again, like you can just write the code, press play, it just runs. So you don't have to do a lot of manual steps anymore. But if you are very hacky kind of person, you want to run something on your own laptop and want to be a little bit more kind of geeky, you can try that. There's a ton of documentation, and there's a lot of sample codes in our public Git repo. So if you do Bodo get Bodo.ai get, you see lots of examples that we have already written, and you can take a look at. So how does it work? Like how did we end up having this much performance improvements? What's the magic? What's the secret sauce? So that's the remainder of the slides. So under the hood, we are using a kind of a technology or like a protocol called MPI. This slide is focused on giving context about what is MPI for people that might not be familiar with it. If you're familiar with it, then fine, you don't have to worry about it. But like MPI is developed in the 90s. It was designed to be an abstraction over kind of complications of a network communication. So it kind of there are different implementations for different languages, but it just makes it easy to reason around nodes and processes in a cluster of machines, right? So there is generally a global rank assigned to nodes, and that's how they know their role and how to find another pieces of data across the cluster. So writing MPI program is widely used in kind of high performance computing field. A lot of programs today that runs in national lab supercomputers somehow use MPI, it's basically a very widely known things in the research and in the supercomputing field, but not across industry, especially for data engineering. One of the reasons could be because the people who can write efficient MPI code needs to be really specialized, and they need to be experts. They need to be familiar with parallel computing, and it's not easy for a lot of companies across industry to build that expertise. So performance in generality is there, but it's not easy to write a code that works. So that's the main challenge. So if you think about kind of a history of kind of a large data processing platforms, like Hadoop was very good at running at scale. It was very good at failure tolerance, but in terms of a performance and scalability, if you think about that axle, it's like MPI is extremely performant, right? And that's at top of the axle. Hadoop is not super performant. It relies on reading from disk, not super fast. And the scale of simplicity also, it's not really easy to write a MapReduce job. That's why there's a lot of abstraction on top of MapReduce. And Spark kind of was a shift toward improvements on both ways, because they find a new programming model that makes it easier to define your task or processing unit. Also, the performance was significantly better because it moved to in-memory. We think Bodo is step function improvements because we are using MPI at the heart of the architecture, which we talk about how it gives us performance improvements and over the distributed system approach. And we are using Python and SQL, which is the kind of a widely known programming languages and models. So how are execution models different? How it's giving us the performance improvements we need? So basically, in the distributed space, like Spark or Dask, there is always this driver or like I know somehow called master nodes that kind of generates lots of tasks, and it basically works as a kind of a center of distribution. And a lot of decisions around networking happens at the runtime. There's a Python code that you need to be, if you have a Python code to serialize code, you need to rewrite it because they generally have the specific programming models. There is certain inefficiencies with this center, like kind of the networking, and also a lot of being blocked on processing happening and the communication across master, driver node, and the executors. In the Bodo mode, though, there is no master, there's no the main driver. So a lot of these networking decisions happens at the compile time versus runtime. That's kind of the major efficiency point. And also your kind of SQL query or Python code just converts into the MPI binary. So a lot of kind of complexities and that in a Spark model is decided during the runtime and cause inefficiency and staleness. It's kind of handled in the compile time for us, and during the runtime we are seeing a lot more kind of CPU utilization, a lot more kind of more bangs for the bucks in terms of getting out more out of course, basically happening in the Bodo cluster versus a Spark cluster. So there's less overhead. So our approach to the compilation process is in ordinary compiler, there is human readable code. You translate it to the machine readable code. Our compiler is slightly different. We are analyzing the high level code structure, not at the if and else and for loop level, but at a kind of a high level component or operator level, and then like group by and join, and try to basically do some parallelization at that level. And then when we have the kind of a semantic figured out, we go and convert it to the machine code or MPI binary executable. So automatic parallelization is the secret sauce of Bodo compiler, basically. So there have been a lot of research in years, and you can find, just Googling it, you'll find a lot of it. Just was an effort to convert a sequential program into a parallel program. Generally, these efforts fail or didn't have a wide success because they were doing it at a scalar level, and it becomes an NP hard problem. It's very difficult to do something like that. And in Python, it's even more complex because there's dynamic dumping. There's a lot more complex data structures. Bodo approach was that focused on high-level APIs, again, like join and group by and data frame level, and then convert these operators into a first-class citizen, and kind of make them embedded into the DSLs. So this high-level semantic kind of helps with parallelization, makes it simpler. That's why we're successful in achieving it. So just a high level of a compiler workflow. We start with a Python function. We produce an intermediate representation or IR, and then we try to do a data frame transform, which basically converts things into time series. In this level, we want to convert as much as possible everything into arrays, which eventually parallel accelerator get some parallelized operations on top of that, and then at the end we do a final distributed analysis, and then produce the final MPI binary, which is a machine runnable code. So on the SQL side, also that was the starting engine of the compiler workflow from Python. So we did something I think brilliant in terms of supporting SQL, which is we are using the exact same compiler workflow, but we are using Apache calcite and produce kind of a logical plan, and then to do a code generation, and then use the exact same workflow to produce the same engine. So that kind of helps us to get a lot of commonalities and efficiencies just by using the same compiler engine for both, supporting both Python and SQL. So I think with that, so this is a high level of like how the system works. So we talked about why customers use Bodo, what's the performance improvement we're providing it, how to interact with Bodo, and what's under the hood. It's basically the compiler technology. From here, we want to talk a little bit about some specific innovations that we had in order to produce the superior performance. And we thought this is more relevant to a performance summit because here we talk about some of the kind of a deep level performance optimizations we have made. So next, Sahil, who is a lead engineer based in Pittsburgh, is going to talk about two of those technologies, like applying Bloom filter and also kind of a different kind of shuffling we have provided using MPI power or magic. And then Nick will, after that, talk about filter pushdown, which is also another innovation we had. So with that, I'll give it to Sahil. Yeah, I can do the clicking, Sahil, if you just tell me.
Okay, great. Thanks for the intro, Ahmad. So yeah, like Ahmad already mentioned, like we pride ourselves on our performance, and then performance is the key kind of value add that Bodo provides. So I'm going to talk about a couple of the things that we do differently and that have kind of provided us with this massive performance improvement. So the first one is shuffle. So most the ETL workloads that you find out there use operations like group by and join. And all of these operations would require one or more shuffles. So let's take this example that's in there. So you read in two data frames, and then you do a merge. And a merge in Pandas is essentially like a join in SQL. So, and then you need to compute the joined output, and then you need to return it out. So to compute this output, let's say you have some columns, a few columns, and then you want to join under, like it says, the column right region key. Let's say there's like 4 different values for region key. And on each rank that Bodo is running, like on multiple processes, each rank reads in various values of region keys. So we don't yet have any separation between what ranks have read what data. So, but to compute the join output, we need to make sure that all the values for one region key end up on the same rank or on the same process, so we can compute the output data frame after the join for those sets of rows. So this requires a lot of some data movement, which like I said, like you need to move all the region keys to the same place. Can we go to the next slide? So different systems do this very differently. So for example, Spark, which is a MapReduce system, like we mentioned, it uses in this case, the driver will schedule a lot of map tasks in which each of the executors will create these intermediate shuffle files and then write them either to disk or keep some of them in memory as much as possible. And then after that, the scheduler will launch, once all of that is done, the scheduler will launch another set of reduced tasks, each of which will kind of go in and read these files. Sometimes they'll have to kind of go to another node and get these files and things like that, and then kind of do the operation after the shuffle. As you can imagine, like this incurs a lot of overheads. So there's a lot of scheduling involved. There's a lot of reading and writing and network transport involved. The way Bodo does shuffle is slightly different. So if we go to the next slide. Yeah, so with Bodo, like we said, we use MPI, and MPI is this magical all-to-all V collective operation, which is essentially a very efficient in-memory shuffle. So what all-to-all V essentially does is you can take data which is organized, let's say, on one rank, and you have some data on every rank. You need to transport it in some order to every other rank. So MPI provides this all-to-all V, which allows us to do that. And as you can see, like there's, Ahmad, can you click once more? Mm-hmm. Yeah. So let's say we have like 4 processors, and each of them have like an array of data, and we need to move the data around so that it ends up looking like the one on right. So like B0 goes from process 1 to process 0, for example. So to do this, there's like, since each rank knows exactly what to do, there's no scheduler overhead involved. And all the processes are working highly synchronously. So there's no delays due to scheduling. And there's no, since it's completely in memory, there's no kind of file movement that needs to be done. So I'm going to walk you through like a very simple algorithm, the textbook algorithm. But in general, there are a lot of algorithms out there that we utilize which are optimized for different network topologies, like based on how your nodes are spread out and how your ranks are spread out on those nodes. For different network interfaces, such as RDMA, for example, different message sizes, and so on and so forth. So let's take a very simple example. So let's say you have, next slide. Yeah, so let's take the most basic kind of algorithm for all-to-all. This algorithm has n steps for n processors, and in the ith step, processor K will receive data from the K minus ith processor and send data to the K plus ith processor. And just imagine it's happening in a modulo fashion, so it can wrap around. So basically, in the first step, you would have each rank would just write to the buffer itself. Like so, A0 goes to A0, B1 goes to B1, and so on and so forth. In the next step, basically we have rank 0 now sends data to rank 1. Rank 1 sends data to rank 2, and so on and so forth. In the next step, it's I equals 2. So rank 0 sends data to rank 2, rank 1 sends data to rank 3, and so on and so forth. And then in the final step, we essentially send data from rank 0 to rank 3, rank 1 to rank 0, and so on and so forth. So basically all your data will end up being shuffled and be exactly where you want it. And this happened without kind of any scheduler overheads and any kind of like memory file creation and things like that. One point to add is that this is an example of an all-to-all, but what we actually use is something called an all-to-all V, which allows where the V actually stands for just variable size buffers. Because in ETL use cases, you might want to move different amounts of data from different ranks to another ranks. And so that's a little bit about shuffle. And now I'm going to talk about something that uses shuffle, that's a join. So in spite of having a very efficient shuffle implementation like we just saw, shuffle still remains the biggest bottleneck in most join operations. So we've made some optimizations to kind of circumvent this. For inner joins in particular, we use something called Bloom filters, which help us reduce the amount of data that needs to be shuffled in the first place. So just as a quick refresher, Bloom filters are essentially like a probabilistic set that's implemented using a bit array. So let's say you have a bit array of size 10, you have you have 2 hash functions, and for every element, you kind of hash them with those 2 hash functions. And for the output, you set the right bits. And then once you've filled the Bloom filter this way, you can go back and query the Bloom filter to ask, okay, is this element in the Bloom filter? If it says yes, there's a pretty good chance that the element will be in there. But obviously, there's a chance for a false positive. And if it says the element is not there, it's definitely not in there. So this kind of fits our use case perfectly. So the way we use this, for example, is we compute the hashes can you go to next slide? So yeah, the way we use this is we compute the hashes for each of the key columns on the shortest table. Because again, the point is that we want to create the smallest Bloom filter possible so that it's efficient and in its lookup and its entry. So we create these Bloom filters locally on every process. So every process owns a chunk of data, and they create these Bloom filters. But now to do the actual filter, we need to create a global Bloom filter out of these local Bloom filters. And for this, we use another MPI operator, a collective operator called an all reduce. And in particular, we use all reduce with the union operators. So as you can see in this kind of example, let's say each rank has a local Bloom filter. We do a all reduced union on this to create a global Bloom filter. And now each rank can filter the other tables based on this Bloom filter before shuffling them at all. So this reduces a lot of cost, and we've seen like this give us massive performance improvements. The last thing I want to touch on is that Bloom filters, as you can imagine, the larger the Bloom filter, the lower false positive rate you can have. But we need to kind of carefully manage the performance of our Bloom filters. So for example, you don't want your Bloom filters to get too large, because at some tipping point, the kind of the improvements that Bloom filter give you kind of are less than the overhead of creating a Bloom filter. So for example, in general, like when you're working with Bloom filters, you have 4 levels, which is kind of how many elements you're going to put in there, what's the false positive probability you're looking for, what's the size, how many kind of hash functions you're going to have, and things like that. So to create like optimal size Bloom filters, we need to know kind of what's the cardinality of our data. And so for that, we use something called as hyperloglog, which we can generate from the hashes that we've already computed for the Bloom filter. And using that, we get a very good estimate of the cardinality. And based on that, we can kind of optimize the probability of false positive rate and the size of the Bloom filters to get to a Bloom filter size that will give us good performance while not being an overhead. The other small thing I'll mention is that Bloom filters are, in general, not very performant and not very cache friendly. So we've had to use blocked Bloom filters, which kind of give us both cache friendliness and some level of SIMD optimizations. And when computing the global Bloom filters, we also make sure to use topologically aware union reduction algorithms so that operation can happen very quickly as well. So yeah, so these are like some of the optimizations that we've done inside Bodo to kind of make Bodo like one of the most performant ETL platforms out there. And now I'm going to hand it over to Nick, who's our lead compiler engineer, who's going to talk a little bit more about filter pushdown.
Thanks, Sahil. Yeah, so when you think about Bodo as being an ETL platform, our compiler does a large portion of the work, and especially it helps to accomplish the simplicity aspect, because as we mentioned earlier, MPI by itself is not a great place to start. So as Sahil mentioned, one of the most important things that you can do for reducing the amount of ETL that's necessary is to reduce data movement. And in particular, I'm going to talk about how we reduce I/O by leveraging metadata from various types of file formats. So the Bodo compiler automatically performs filter pushdown and column pruning. If you're not familiar what those are, filter pushdown is the process of taking a filter, like you see on the left, there's a greater than or equal to ended with a greater than. That would be an example of a filter. And rather than executing it after loading the data, you push it directly into the I/O step, and then you perform some optimizations in order to make sure that that's done efficiently. And then column pruning is a similar idea, except you only load a subset of the columns that you actually need. And Bodo is able to do these on high-level Python APIs, including a variety of changes that could occur. So we see an example here of one filter pushdown that we can perform. Here we took a scalar that we ended up computing. We pushed that before the IO step, still using the high-level pandas functions. And then we took the pandas steps that involve the actual filter pushdowns. We pushed those into the IO steps themselves in order to make sure that they're done efficiently and productively. We can go to the next slide. And to reinforce what Ahmad mentioned earlier, the compute engine, we're not just a particular storage solution. And that means we work with a variety of different formats. And in each of those, we have a unique and performant way to optimally perform filter pushdown inside of Bodo. And I'm going to cover a couple of those here today. I'm going to talk about Parquet, followed by Iceberg, and finally Snowflake. So starting with Parquet, if you're not familiar with Parquet, it's a particularly efficient file format that's really good for column-based data. It keeps data separately in columns, and it groups common rows together into a set that we're going to call a row group. So for that, the Bodo Parquet filtering process is a two-step process. So the first step, we interact with something called hive partitioning. If you're not familiar with this is basically a process by which a particular column value is the name of the directory, and then all of the files that are found within that directory share that one common value. And this can be done to prune large number of files that we need to look at. So as an example here on the left, if we had two directories, A equals 1 and A equals 5, if our filter was A greater than 1, we know that we can skip looking at all of the files inside A equals 1 because it fails our filter. And then once we've narrowed down the set of files, in parallel, we reference the advantages of the Parquet file format in order to perform more efficient filters. So these groups of rows, they have some column statistics that are held per column, and that can enable us to skip looking at large chunks of the data. So for example, a row group inside of F3 might have 3, and because we're looking for B less than 2, we know that no value inside of this row group will satisfy the criteria, and we can skip loading all of that data without looking at it. And then at the end result of all of this, there will be some groups we'll need to look into, and for those, we'll perform some actual filtering. Moving forward to Iceberg, what you'll see is that Iceberg is different than Parquet because it's a very new format. If you haven't heard of Iceberg, it's really cool. I recommend checking it out. Basically, Iceberg enables some really cool operations such as schema evolution, where you kind of get to grow how your table changes over time. And it does this also with hidden partitioning. So your partitioning schema can grow as your data grows. So if you're partitioning by year and then your data size grows, eventually you're partitioning by day. And in the process of doing this, Iceberg handles a lot of these details so that you don't have the rigidness of an example like hive partitioning. And it also contains file statistic information in sort of its metadata. So Bodo leverages this metadata information that Iceberg stores in order to apply the filters directly to it. And taking those filters and applying the various Iceberg transformations, we're able to then return a list of the files that may end up being what we need to look into. And then once we've gotten to this stage, the remaining files are often Parquet files. And those Parquet files themselves can then be checked the same process as before, looking at particular row groups to see which of the row groups apply and ruling out those chunks afterwards before finally, as always, just looking at applying to the filters to the remaining set of data. And in this way, we minimize the amount of data that you need to read with Iceberg. Finally, moving on to the next slide. We also have support for filter pushdown inside of Snowflake, but Snowflake is very different to how we handle things like Parquet and Iceberg. So in particular, Bodo has a partnership with Snowflake. They're one of our investors, but we don't do the compute inside of Snowflake, except when it's the most efficient. Instead, Bodo is the compute engine, and we're loading data from Snowflake itself before performing the compute on a cluster inside of, say, your VPC. And in the process of doing this, the user will provide some query to load the data from Snowflake, which could be as simple as select star from line item, which if you did that in a normal Python setting would be very bad because you get a huge amount of data and it'd be very expensive. But Bodo is able to use the compiler information to put the column pruning and filter pushdown directly into the queries that are being submitted into Snowflake. So in this example here, we were able to detect that only one column ends up being necessary. So we only load a single column from Snowflake. And in addition, the starts with operation and ordered with the equality, both of those can be computed more efficiently inside of Snowflake because Snowflake may be able to leverage the internal clustering information to make its query more efficient, and then additionally reduce the amount of data that actually needs to be transferred from Snowflake. And so in this particular example, we've put a lot of the compute directly into Snowflake, but in a more realistic use case, we would put the steps that are most efficient for pruning the IO, and then the compute heavy workloads would be done inside of Bodo. Moving to the next slide. So as we also, Ahmad mentioned earlier, Bodo has support for both Python and SQL inputs. And these types of optimizations work for both use cases. So on the left, we have some example Python code, it's the exact example from before. On the right, we have an example where you might basically give a data frame to run inside of Bodo SQL, and then you'd execute a SQL query. And in this situation as well, Bodo is able to distinguish the compute that should be done on the cluster itself from the compute filtering, column pruning that should be done inside of Snowflake. And in this example, you would result in the same exact query that's being run inside of Snowflake, regardless of the language being chosen. And finally, if we can move on to the last slide. Another advantage of having this one common compiler is that we actually get the ability to perform optimizations across our various language boundaries. So I have an example here, again, relatively simple example that shows how we can utilize column pruning and dead code elimination across this SQL to Python boundary. So here we have an example where we would load two columns in SQL, and in one of them we're performing a transformation to convert all the data to uppercase values based on some filter. But then it gets passed into the Python step, and the Python actually only needs a subset of the data, which could happen when you're integrating various modules together, as an example. And so in this case, Bodo is able to detect that only L order key is actually needed. It eliminates the steps of the SQL query that are not necessary based on that Python information, and actually is able to propagate it all the way back to the IO step. So in this example, we're still applying the filter that comes from the SQL step, but we're loading just the singular column that is needed by Python in order to give us the most efficient result. And this actually has further optimizations as well that we are able to do by having two different languages. One that we're particularly happy with is typically when you have two distinct languages like SQL and Python, it becomes a runtime decision to find problems inside of like type mismatch information with your SQL query. So in a traditional Python setup, you would say execute the SQL query, then you compare to the Python types and you find out that things didn't work. But because we have one shared compiler, we're able to detect those typing issues at compile time and prevent the time wasted and the costs associated with needing that SQL query to execute. Okay, moving on to the next slide. So we've talked a good amount about some of the work that we've done so far. There's also a lot of work that we want to do moving forward. So some of the things that we're looking to do in the future is to expand our platform to support scheduling batch jobs. We want to continue to optimize our query engine and our memory management process to reduce the amount of memory that we need and more efficiently manage sets on smaller clusters. We have a compiler that enables us to have really efficient compute, but it's a continual effort to kind of reduce our compilation time and make sure it's as efficient as possible. We want to continue increasing our coverage and support for the Python and SQL languages, as well as we eventually want GCP integration, and we'd like a complete developer experience to be happening with Bodo, where we could manage the entire process, going all the way from data processing through compute, monitoring, and integration. And if any of those seem appealing to you whatsoever, we're always looking for new people to join us, and we'd be happy to have any of you come on board. All right. So thanks so much. If you have any questions, we'd love to answer them. Also, we have a link here. This is to our website, is the first one. And the second one is a link to our platform where you can get started and give Bodo a try, as Ahmad mentioned earlier.
Thanks, Nick. Thanks, all. Yeah, open up for questions.
Yeah, thank you so much for the talk. It's a great continuation of the previous talk also, and a lot of awesome magic. So I wonder, since we're like, when it comes to big data, some of the properties that we tend to expect from regular programming environments, like correctness, do not necessarily apply as much in big data processing, because first of all, I guess we expect some sort of eventual consistency most of the time, just because, I mean, like as query executes, there is already some sort of lag. You basically do not see the latest data anyways. So I think there is a lot more opportunity for imprecision when it comes to gaining some extra performance. So I wonder if you have some ways to request to bound the error and provide extra performance by using probabilistic data structures. So you mentioned you're using Bloom filter, but you don't use it to affect correctness. But there are things like, for example, count mean sketches and all sorts of other sketches that can be used to provide pretty good estimate, potentially bounded, for extra performance. So I wonder if you're using some of those techniques.
So I think initially you mentioned about like kind of a data correctness, eventual consistency. So that kind of like brings us to toward a kind of a near real-time data processing. And like there's also another aspect of data processing, which correctness is super important, is like batch processing. Is just like the data is there, and you're not talking about the kind of live changing data. A lot of our use cases right now are on the realm of like kind of a batch processing. But also it's an interesting challenge for us to look into kind of a CDC and kind of a real-time processing data. So I think you had a good point around applying things like Bloom filter in gaining performance in terms of like especially this is along the line of filter pushdown. If you reduce the amount of data you need to process and read on the data IO layer, that saves a lot of compute time. Is that what you are asking about, or?
Yeah, there are just a lot of techniques. Like, for example, you mentioned hyperlog log, which is frequently used to estimate number of distinct elements, let's say. So it's not precise, but it's way faster. So you're gaining a lot of performance by trading a little bit, or at least a bounded amount of error. So I just wonder if there is some way for you to just say, okay, like I'm willing to accept, let's say 10% imprecision, but instead I'm gonna get like, 10x improvement.
Do you have some thoughts on that? So so today we don't have that kind of like concept in, but I think we need to work with customers to understand if that approximation is acceptable. It depends what kind of a workload we are working with. If it's a kind of like a manufacturing workload or banking workload, this is completely different, and requirements are very different. Correctness becomes requirements can be slightly different. So I think it's an interesting idea, and we should think about it. And I think, but today we don't have something like that.
I see. It's just oftentimes there are just APIs that can explicitly tell you, for example, like approx distinct, which means that like it's a distinct, but it's approximate. So customers are not fooled to believe that you're going to get the absolute exact number. Exactly. But they know that they should expect some sort of gains in turn. And the same thing when you query, let's say when you have a distributed setting, there is pretty much always some strugglers. So you can just say that, like, I don't want to wait for those strugglers. Obviously, we're going to lose some data because we don't get those results from a few machines that are just, taking forever basically to compute. But at the same time, you bound the latency.
Execution time. Yeah.
Right.
Yeah.
So just to add on, kind of basically, as we said, like we're a compiler, so kind of we need to stay within the bounds of what the APIs allows us. So like you mentioned, like there are a lot of APIs that allow us to do this. And so for example, in SQL, there's a lot of approx kind of APIs. And so we will be definitely adding support for them. And these, like the optimizations that you mentioned, these are the kind of optimizations we would use when we're supporting those APIs. But since we are not creating our own APIs at this point and we're a compiler, we need to kind of respect the guarantees that the existing APIs give us. So when it comes to those SQL APIs, we'll definitely be doing that. But for the regular APIs, we don't make those kind of approximation decisions at least at this point.
I see. And one more question. So there are lots of efforts on standardization when it comes to storage in big data processing, like the Parquet, for example. But I wonder if there are some similar efforts to standardize on the algorithms or APIs that are used to perform these big data analysis so that you can reuse them, because obviously there are so many systems, like people are using similar things in Spark, similar things in NumPy and Bodo, and like many others. So I wonder if there are any efforts to actually standardize those APIs so that there is more coordination around implementing the runtimes instead of building the APIs from scratch every time.
Yes, so absolutely there are. I believe there's a regular data APIs call. I don't attend this, but I believe one of my coworkers does attend roughly every 2 weeks, and they discuss sort of like the goal of kind of like unifying the pandas, the NumPy, the general like data frame array-based APIs under some like common API that can be shared. And we have we financially have some backed that effort, and we're strongly in favor of it. In addition, our product is based around like we don't want to introduce APIs unless it's absolutely necessary. So our focus is to make sure that even if maybe there's not another product out there that can make pandas work as well as we can, you'll get that same common pandas API that you're familiar with. So you're not bound to the product itself. You're not converting all of your code over to like something that like doesn't translate anywhere else. You're using some common set of APIs, and as those standardize, Bodo will get to be the standard as well. That's our hope.
It's just, it seems like, I mean, don't get me wrong, I've used SQL and I guess most of the people are familiar with it, but at the same time, sometimes it seems like we are trying to fit the round thing in a square hole or something, like basically not always a great fit for the processing needs that we have, but we just have to use the APIs and tools that are available, and then we have to do a ton of magic on the compiler side to infer what was actually meant by those APIs and reprocess them. So there is a lot of waste, I guess, in terms of both optimization opportunities and overhead for processing these things over and over again.
And then there are certain things that it's actually good for. And the good thing about Bodo is that we're thinking about an experience that you can have this imperative nature of Python, mix it with SQL, and have this kind of a mixed experience in terms of development. So you can run a query, take the data frame, do some Python on top of it, and that should be the kind of a more powerful way of express your business problem. And we think if we increase our coverage on Panda, NumPy, kind of improve our Python support and have a full SQL support, I think it will be an awesome experience.
Yeah, sounds great. Well, thank you so much.